Good morning. Let's start our lecture. The main topic of our today's lecture is Euclidean spaces. We began to study this topic on the last lecture, and first of all, I briefly recall the main notion and main results of last lecture. I recall that main idea, definition of the Scala product is following. We try to naturally generalize the notion of dot product. I recall that dot product one hand is defined by angle and distance in the geometrical vector space, but from other hand, itself angle and distance can be defined in terms of dot product. Dot product defined in the geometrical vector space. We try to transfer this definition on the general case of the arbitrary vector space. But in this case, we need to define independently this notion independently, and we introduce the some independent construction which is called Scala product. Namely, Scala product is assignment, is the following assignment. We have arbitrary vector space V, our real field number R, and we define the following map or following assignment, which assign to the ordering pair of the vectors from this vector space V some real numbers. We have two vectors V1 and V2, and we obtain, apply these assignments, some real numbers which we denote by the following way, and we call the Scala product of this vector V1 and V2. And this assignment must satisfy to the following condition. First condition, 1, Scala product 1. The so-called commutativity. If we have two vectors V and U, and the assignment VU is equal UV, the so-called commutativity condition. Second condition, so-called linearity condition. If we apply U and to the sum arbitrary vectors V and W, we obtain the Scala product UV plus UW. This condition this condition is true for any vectors U, V, W from the vector space V. And third condition, if you have any real number x, and we apply our scalar product to the product scalar x and arbitrary vector u and any vector v, we obtain the product scalar x on the scalar product vectors u and v, and is equal scalar product u and product x and v. This three condition is defined. This three condition define a scalar product, but we have some complementary condition for so-called positivity condition, namely the scalar square of the any vector v greater or equal 0 from any vector v from v, and so-called scalar square v strictly greater than 0 if v is not equal 0. And if last condition is fulfilled, we have deal with so-called positive defined scalar product. If the last condition is not fulfilled, we have deal with so-called indefinite scalar product. But in any example, we have deal with positive definite, positive defined scalar product. And this scalar product, as is mentioned above, is natural generalization of dot product. And we have this definition on the last lecture, this main definition of this topic. And we consider the following example of Euclidean space, or of Euclidean structure and Euclidean spaces. Example 1. Let V is Rn. I recall that the element of this vector space is n tuples x1 and so on xn, and entities of this n tuples are real numbers. And we will use the capital letters. We will denote by this capital letters the elements of this vector space, and we can define scalar product to such vectors as dot product of these vectors, namely as sum of the product of the corresponding entities of elements of these n tuples. If we have initial vector space, if we have that the n, the size of these n tuples equal 2 or 3, we have deal the coordinate presentation of the geometrical vector space, and this scalar product coincide with dot product. on this geometrical vector space. Moreover, we defined the dot product on the arithmetical vector space by this formula, and in this example the Scala product coincides with dot product. And example 2, let V be the space of continuous real valued function. Real valued function f, which defined on the interval or segment, maybe segment, minus a. Some vector space of such a continuous function. Easy to see that these functions form vector space, because the sum of continuous function is a continuum function, and the product of such continuous function on arbitrary scalar lambda is also a continuous function. This vector space, we can consider this vector space as some continuous analog of the previous example, because the correspondence, the point of segment and value of this function is natural generalization of the correspondence coordinates and value of coordinates. In this case, we have infinitely many coordinates, in some sense, in non-state sense, and this space is example of so-called infinitely dimensional vector space, and we can define the Scala structure, the Scala product, by the following formula: integral, and the boundary of value of integral is endpoint of this segment, and integral our product ft gt dt. Easy to see, this formula and this have the same nature. In this formula we have sum, and we have finite numbers of coordinates. In this case, we have a deal with continuous function, and the argument of this function is some counterpart of coordinates in the first example, and we change the finite sum on the infinite sum or integral with some continuous analog of this function. Easier to check the first three axioms. Easy to see that this Scala product is symmetric. Easy to see also that this Scala product is satisfy condition SP2 linearity, and third condition homogeneity. And we can easy to check this condition, but more hard to check that this Scala product is positive defined, the condition of positivity. Namely, we need to check the following condition: the Scala product f square t dt strictly less than 0 if f of t is not identical 0. The main idea to check this condition is the following: if we have some non-zero function. What does mean non-zero function? We have some point which belongs the interval of domain for this function f, namely the interval minus a, such that the value of our function is this point strictly larger than 0. And we can choose some neighborhood of this point, namely x0 minus epsilon, x0 plus epsilon, such, maybe delta, excuse me, maybe delta, such that for any point x from this interval, the value of our function strictly greater than half epsilon. The existence such neighborhood, it follows from definition of continuity. This function is corollary of the fact that this function is continuous. And we have the following evident condition: the value of the integral, which we consider r as a all segment minus a, greater or equal than values of this integral, our the segment with endpoint x0 minus delta, x0 plus delta. And using this equality, we have that this the value of the last integral strictly greater than integral which we consider from the minimum of this function. And we obtain we suppose that our initial function is not identical, is not equal, identical 0, and from this fact it follows that this scalar square of this function is strictly greater than 0. And we prove that for this scalar product, the last condition of positivity is true. And we obtain that in this case we have deal with positive defined scalar product. And that's the main topic, the main construction which was considered on the last lecture. And from this point we began the new topic and introduce some new notion. Maybe you have some question. Any question? Do you understand? Do you understand that the main definition and examples? No question? Oh, yes. Okay. If you understand, let's continue. And I consider the next natural notion of orthogonality. I recall if we have two vectors of the geometrical vector space, for example, u and v, and if its dot product is equal 0, we say that these two vectors are perpendicular, and we use the notation u perpendicular v. I recall that the dot product is defined as a product of lengths of these vectors on the cosine of angle between these vectors. And easy to see, if we have a deal with non-zero vectors, this dot product of these vectors is equal 0 if and only if cosine of angle phi between these vectors is 90 degrees or direct. This angle phi is direct angle. And it means that these two vectors are perpendicular. We can use this analogy and define the orthogonal vectors, perpendicular vector, we can see that two vectors u and v, which belongs vector space V, are orthogonal if and only if its scalar product is equal 0. In the arbitrary vector space, we have not initial notions of angle and on the length of the vector. We have only scalar product, which defined by abstract condition. But using this abstract notion, we can introduce first the notion of orthogonality, and we can tell that some arbitrary vectors are orthogonal or perpendicular if its scalar product is equal 0. And we can introduce independently the notion of the length or of the norm of arbitrary vector. We have the norm. Norm of the vector is a natural generalization of the notion of the length. We define the norm of vector v as a root square from scalar square of this vector. From the last axiom, as before, it follows that scalar product is positive, and we can correctly define the root square from these positive numbers, and the root square from scalar square we will call the norm of the vector, and we can define also the angle between two vectors, the cosine of the angle we can define by the following condition: the ratio of scalar product of these vectors and product of the norms of these vectors. And phi is an angle between vectors u and v. For example, if you consider the continuous function, and if you, for example, let our function f t is equal t, and we can define the norm of this function in this abstract vector space. If you have such scalar product which is defined by this formula. For example, we have scalar product which defined by, for example, we have the space, let V be the vector space of continuous function which defined on the segment -1, 1, and the scalar product function is defined by the following formula. The equation: let we have function f is equal t. What's the norm of this function? Norm is analog of length, and the length of the function is not defined notion, but the norm can be defined by the previous formula, and we can define the norm as a root square from scalar square of this function, and by definition we obtain that the norm, first of all, let's calculate the square of this norm, and we obtain the following expression. And easy to see that we obtain the ratio 2:3 from the scalar square of this function. From this equality, we obtain the norm of this function t is equal root square from the ratio 2:3. And in this case, we can define norm of function, and we can say about length of the function. In the same way, we also can define the angle between two functions, between two continuous functions. Easy to see that the notion of the norm and the length is depend from the Scala product. We can introduce the Scala product by the different formulas, and in this case we obtain different Euclidean spaces, and in these Euclidean spaces, in these different vector spaces, the function can be has the different norms, and we can obtain that if you fix two functions and consider the angle between these two functions in different Euclidean spaces, but as vector spaces are coincide, we can obtain the different value from the angle between these two functions, and it means that the Euclidean space is defined by the Scala product. We have the pair vector space and Euclidean structure. Euclidean space is equal pair vector space and Euclidean structure of Scala product. We can define the following notion in the vector space. If we have some subset, let C be some subset of Euclidean space V, and we can define the following subset as perpendicular, as orthogonal, as the set of all vector u from V such that this vector u are orthogonal to the vector V from any V from S. Easy to see that this set actually is a vector subspace of V. We can easy to check if we have two vectors u1 and u2 which belong S. From this it follows that its sum is also S perpendicular. That its sum u1 plus u2 as also belong as perpendicular. Really, if you consider Scala product of this two vector u1 plus u2 and arbitrary vector v from S, we obtain, using the property 2 of Scala product, we obtain that this sum is equal the sum of Scala products u1 v plus u2 v. But by definition, u1 belongs as perpendicular, and it means that this Scala product is equal 0, and u belongs also to as perpendicular, and it means that the second Scala product is also equal 0, and we obtain 0 plus 0 is equal 0. And we checked this property. And second property, if u belong as perpendicular and any real number x, we have Scala product xu and v is equal product x, u and v. And u belongs as perpendicular, and it means that the Scala product is equal 0. And the product of arbitrary scalar x and 0 vector 0 is equal 0. And we obtain that this set as perpendicular is vector subspace of vector space V. Vector space V. Easy to see that if vector u subspace as perpendicular, and this vector perpendicular any vector v, from this fact it follows that u perpendicular to the any vector v from any vector v from the linear span of S. And this assertion of the following proposition. Let S some subspace of the vector space V. S perpendicular is equal perpendicular of the linear span of the S. Easier to see that if we have two vectors v1 and v2, which belong from S perpendicular, and it means I'm sorry, we have let v1 and V2 to vectors which belong S, and let U is an arbitrary vector which belongs to S perpendicular. Easy to see that if U belongs S perpendicular, it means Scala product U V1 is equal 0, U V2 is equal 0. And from this fact, we obtain that U perpendicular the sum of these two vectors. And also we obtain that U is perpendicular the product Ux V from any real number x and any vector V from S. From this fact, we obtain that if we have two vectors U1, U2, which belong as perpendicular, these vectors S belongs the perpendicular to the linear span of these vectors. And from this we obtain that S perpendicular belongs to the linear span S perpendicular. The inverse inclusion is evident, because if we have inclusion S1 and S2, from this easy to see that it follows that S2 perpendicular belong is one perpendicular. We have the following evident inclusion: S belongs to this is linear span, and from this fact it follows that perpendicular to S span is contains into S perpendicular, and we obtain, compare these two inclusions, embedding, we obtain that this equality is proved. And if we consider this definition, we can see some analogy between the definition of S perpendicular and annihilator of subspace, which was introduced before. What mean this analogy? Let's consider in detail this analogy. I recall that on the one of the previous lecture we introduced the notion of so-called dual space, or space of functionals on the arbitrary vector space. Let's now suppose that initial vector space is the Euclidean vector space, and let V be Euclidean vector space. We can introduce the following map from V to the dual vector space V star. Namely, we can assign to the vector V the functional which we denote by f sub V, and which defined by the following equality: the value fv on the arbitrary vector u is equal Scala product vu. Easy to see that this functional is linear functional, because if you apply this functional to the sum of the vectors u1 plus u2, you obtain, by definition, which value is equal the value of the Scala product u and u1 and u2. And using the property of linearity, we obtain that the last expression is equal equal to the sum of the scalar products vu1 plus vu2, and by definition is equal fv u1 plus fv u2. And we checked the condition of linearity. We can also write some scalar x and consider the sum of the product xu1 plus xu2, and we insert x on this place, x, and can transform this inequality using the condition of homogeneity. We obtain that this last equality is equal x times v u1 plus v u2, and we obtain x f v u1 plus f v u2. And we checked condition which defined the linear functional, and we obtain that the functional which defined by this formula is a linear functional, and we construct some maps from vector space V to the dual vector space V star. Easy to see that this linear map is isomorphism. Easy to see that this linear map is injective map. It means that if our Scala product Vu is equal 0 from all vectors u, it means that V is equal 0, because from this fact, suppose that u is in detail. Let's check that this assignment is injective assignment. We suppose that some vector v, we map this assignment assigned to the sum vector v is zero functional. Is zero functional. It means that this functional, which we apply this functional to the if we apply this functional to the any vector u, we obtain 0. It means that vu is equal 0 for any vector u from v. But it means that and v is equal 0. And from the last fact, using the last condition SP4, we obtain that v is equal 0. So if this assignment assigned to some vector v 0, it means that v is equal 0. It means that this assignment is injective mappings, injective mapping from v to the v star. Easy to see that this this assignment is surjective. If you have any functionals f, this functional is uniquely defined by its values from the sum basis on the vector space v, and we can correspond this functional, which defined by these values on the vectors of the basis. But let's consider the basis u1, un of vector space, and let f be the arbitrary functional, and we have some values alpha 1, alpha n, the value of these functionals. And easy to see that using this equality, we obtain we uniquely define vector v such that v u1 alpha 1 v un is alpha n. This linear system has uniquely defined solution because this linear equation can be uniquely solved. Just later we in detail consider this assertion, and I will give a more simple proof of this fact. But from this we need to some convenient and important construction of orthogonal basis, and we consider the construction of orthogonalization. And using this construction, the last fact of surjectivity of these mappings will be evident. Maybe Any question about previous example? And maybe I repeat the main idea. The main idea is the following. If we have a Euclidean vector space, the Euclidean structure of Scala product is uniquely defined, corresponding or assignments between vectors of the initial vector space V and functionals of the dual vector space V star. And this correspondence assign to the any vector V to the functional of the dual vector space. This functional is defined, the action of this functional is defined as the Scala product of the vector V and vector U. And we obtain assignments between vectors and functional. And we can consider any vector initial Euclidean vector space as a functional which belongs to the dual vector space. And this correspondence is a natural correspondence. I recall that this correspondence was defined by choosing of the so-called dual basis. What does mean in our case dual basis? I proved that this correspondence is isomorphism using some theorem on unique of existence of unique solutions, some system, some linear system. But in the case of functional, we consider so-called dual basis. I recall that the dual basis, the basis of the dual vector space EI, such that if we apply functional EI to the vector of the basis in the vector space V, Ig, we obtain 1 if I is equal j and 0 if I is not equal j. And such basis is called dual basis. But what does mean in our space? What does mean dual basis? We must obtain some vector V such that if we have some basis U1, Un, we can consider the dual basis V such as vector Vi Uj is equal 1 if I is not j and if I is equal j and 0 if I is not j. And we can obtain this basis to prove that this system is has uniquely defined solution. But we can consider more interesting situation. Now we construct such basis E1, En such that the Scala product of the different vectors of this basis is equal 0, and Scala square of this vector is equal 1. Such basis is called orthonormal basis. Orthonormal basis. But if we have only second condition, the second condition, it means that any different vectors of this basis are orthogonal or perpendicular. And in this case, we have deal with so-called orthogonal basis. And the next topic, how to get the orthogonal basis. And we consider the following procedure, the procedure of orthogonalization. This procedure gives us orthogonal basis. The procedure how to construct orthogonal basis. Orthogonal basis. But before this construction, we prove some auxiliary, two auxiliary proposition, and some definition. We will say the two vectors, vectors u and v are orthogonal or perpendicular. Are called orthogonal or perpendicular if its Scala product is equal 0. And we will say that vector v is a unit vector if its norm is equal 0. Is equal 0. And we have the following auxiliary proposition. Proposition 2. If two vectors v and w are perpendicular, then the square of the norm of the sum these vectors is equal sum of the squares of the norm of these vectors. Can you hear before this theorem? What does mean this theorem? Do you understand what this theorem means in the case of the geometrical vector space? Yes, this so-called Pythagorean theorem. If you have two vectors, this vector v and this vector w, and the sum of these vectors, easy to see, is a hypotenuse of these direct triangles. and the square of length of hypotenuse is equal to the sum of squares of these other sides. And but this theorem is natural generalization of Pythagorean theorem, and the proof of this theorem is enough evident. The left hand of this equality is the scalar square of this vector. And we obtain, and after them we can use the property of Scala product, and we obtain that the last expression is equal and we can apply the property 2, also apply the property 2, and we obtain the following equality. But vectors u and w and v are perpendicular, and it means that its scalar products are equal 0, and the scalar square of this vector is equal square of the norms of this. And this proposition is proved. This proposition is proved. And proposition 3. Proposition 3. Proposition 3. For any vectors v and w, we have the following equality. The second equality is enough evident. Maybe this easy exercise, but I proved this equality also. By definition, is equal using the property of the Scala product and repeat this reasoning on the proof in the proof of the previous theorem, we can rewrite this equality in this form. But using the property 1, that the Scala product is symmetric, we obtain that this expression is equal following scalar square v plus twice vw plus WW. And this expression using this formula and change the sign on this term, we obtain this expression is equal and we have two terms which are opposite, and as a result we obtain the following: this term and this term gives us the twice scalar square, and this one and this one also gives us twice scalar square, and we obtain the twice sum of squares of norms of these vectors, and this proposition is proved. And now we can consider the important procedure, so-called orthogonalization of the vectors. What does mean this procedure? We have some basis v1, vn of the vector space V, and our claim to obtain some orthogonal basis u1, un. Arbitrary basis. And this transformation from transformation of arbitrary basis to the orthonormal basis is called orthogonalization. What's the idea of this procedure? First of all, we suppose that we have basis of the two-dimensional vector space, and let we have v1, v2, some arbitrary basis. The idea is following. Suppose let's consider the so-called projection of the second vectors on the two vectors, and the projection is these vectors. If we subtract from the initial vector v2 the projection v2 on v1, we obtain the vector which will be orthogonal to the vector v1. Namely, let projection v2 no v1 is this vector which we call u1, and we can define u1 as v1, and u2 we can define as a difference between v2 and projection v2 on v1. And we obtain that this two vectors are orthogonal. And after them, if we have some arbitrary basis in three-dimensional vector space, we can define, first of all, vector v1 is vector v1. u2 we can define as a difference between v1 and projection v2 on the v1, and u3 we can obtain v3 minus projection v3 on u1 minus projection v3 on u2. And in this I can change v1 on u1, and so on, and so on. Step by step, using this approach, we can obtain the orthogonal basis in the vector space V. But we need to define this projection. What does mean a projection V2 on the vector V1? We can define this projection by the following way, using a Scala product as a ratio V2 V1 is defined V1 V1, and multiply on the vector V1, and this exactly we exactly obtain the projection V1 on the projection V2 on the V1, we can check that the vector which defined by this formula is actually orthogonal to the vector u2. Easy to see that this Scala product, by definition, u1 v1 minus v2 v1 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 defined v1. If you substitute this expression to this formula and using the property of the Scala product, we obtain the following equality: the Scala product v1 v2 v1 minus v1 v2 v1 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 times v1 v1, and we obtain 0. The same way, easy to check that these all vectors are orthogonal, and we obtain the idea of the procedure which gives us the orthogonal basis. But now we try to give a strict proof of this fact. First of all, I consider some relation between arbitrary Scala product and dot product. And this relation help us to calculate in some examples, maybe in arbitrary examples, orthogonal basis. The idea is following. Let u1 un be orthogonal basis such that all vectors of this basis are unit. Such basis is called orthonormal basis. We suppose that we have two vectors, u and we have decomposition of these vectors, vectors v, excuse me, denote the notation v, vector v, and we have the decomposition of this vector in terms of the basis u. And we have other vectors w, and we have the same decomposition in terms of the basic vector. And let's calculate the scalar product of these two vectors. We substitute this decomposition into scalar product, and we obtain using properties of linearity and homogeneity of the scalar product, we obtain the following expression: double sum by I and j, the pairwise product vi wj and scalar product uy uj. But orthonormal basis can be defined the following formula: ui uj scalar product is equal 1 if I is equal j and 0 if I is not equal j. And the last formula can be rewritten in the following form: the sum by only one indices I, vi wi. And this formula gives us exactly dot product of coordinates of this vector. And if we have orthonormal basis, we can reduce the problem of calculation of scalar product to the problem of calculation of the dot product. Other word, the scalar product can be reduced to the dot product if we choose the basis as the orthonormal basis. And now I have maybe 1-2 minutes to formulate the main theorem about orthogonalization procedure. But proof of this theorem in detail I will give in the next lecture. I have no time to consider this proof in detail, but this detail will be important for us, and I prove this theorem later. Let V be a finite dimensional vector space. With a positive definite Scala product. Let W be a subspace of V, and let W1, Wm be an orthogonal basis of W. If W is not equal to V, then there exist vectors Wn plus 1, Wn of V such that W1, Wm, Wm plus 1, Wm is an orthogonal basis of this main theorem will be proved on the next lecture. One remark: in this theorem, we can suppose that this set is empty and W is zero subspace. And in this case, we obtain the procedure to construct orthogonal basis in arbitrary vector space and arbitrary Euclidean vector space. I have no time to continue, and maybe any question about. I explained the idea of proof this theorem, but in the next lecture I will give the strict proof of this theorem using induction, and we consider the examples of application of this procedure to construct orthogonal basis in some vector Euclidean spaces, Thank you for your attention. Thank you. Bye.